So good morning, everybody, to another webinar in the webinar series of Frantak Nexus and Dolores on aquaponics, aquaculture, and hydroponics. Today, we will have a look at improving nutrient use efficiency in the context of aquaponics. And hang on a second. Here we go. You already know me, and you also already had once Carlos Espinal, who is again one of our experts who will add to our experience from his side. He's an innovation director at Landing Aquaculture and responsible for the design and engineering, construction of aquaculture facilities. And in this role, he also has to do with the different aspects of components in aquaculture that deal with nutrient use efficiency. So he will certainly have some valuable insights for us. What we will do today is we will look at the meaning and importance of nutrient use efficiency in the first part of the webinar. We will look at how we can improve nutrient use efficiency going from aquaculture through aquaponics to more sophisticated solutions. We will look a little bit into anaerobic digestion in aquaponics and how these systems can be integrated in our aquaponic systems. And then we will, at the end, have a short look at a simplified anaerobic digestion solution that you could use for small scale or simple aquaponics. So what's the meaning and importance of nutrient use efficiency? The most common metric for nutrient use efficiency is just to look how much nutrients of a given type are put into a system and how much of the nutrients are going actually in productive produce or retained by organisms like fish or plants. So the easy formula would be nutrient use divided by nutrient input multiplied by 100 as a percentage of the nutrient use efficiency. Nutrient use efficiency is important because it's an indicator on how great the environmental impact of a system might be. So if you're not using a lot of the nutrients you're given into a system, the remaining nutrients might be run off into water or create algae bloom in this and damage the habitat of other organisms. It's also an indicator for cost efficiency, because if you have a lower nutrient use efficiency, that means that you spend a lot of money for nutrients that are in the end not used. And they also are important in the context of the sustainability of a system, because, for example, a higher nutrient use efficiency reduces the strain on our resources. And especially in the context of the Sustainable Development Goals, if you look at some of the metrics that are oftentimes used to assess if certain Sustainable Development Goals are met, we can see that, for example, for the Development Goal 2, no hunger, current metrics are plant yield per square meter or a feed conversion ratio or nutrient use efficiency to measure how effective a system produces food. In the context of the Development Goal 6, clean water and sanitation, we see that water use efficiency is oftentimes a metric used to evaluate production methods, but also waste recovery efficiency is another metric. And that's, in our case, mainly the same that nutrient use efficiency, because if we have a high nutrient use efficiency, this means usually that we have a good waste recovery and also with respect to the carbon dynamics, a lower carbon footprint. Then development goal 12, responsible consumption and production. Here also we oftentimes use water use efficiency as a metric. Also feed conversion ratio is mentioned. But again, here waste recovery efficiency and overall system efficiency are very common metrics, where overall system efficiency does not only look at nutrient use efficiency, but also at water use efficiency and energy use efficiency as a whole. And in the case of the development goal 14, again, waste recovery efficiency is very important, and sometimes also fish and plant health indicators. And all of these development goals are addressed by aquaponics, and that's why we also say, and I already mentioned this in an earlier webinar, that aquaponics are multi-solving, because they address not only these 4, but up to 11 sustainable development goals at the same time. And as we can see in many of them, nutrient use efficiency plays an important role. So it might be worth to have a closer look at that to try to understand better what it means. The challenges with nutrient use in aquaculture are mainly that we have a lot of nutrients that go into waste if we only look at aquaculture. And here I took another example that we already looked at when we did the balancing for aquaponic systems, where we can see that of a feed that has around 72 grams of nitrogen per kilogram of feed and 10 grams of phosphorus per kilogram of feed, in the end, with certain assumptions regarding the consumption of the feed and the digestibility, we find out that about 65% of both of the nutrients are excreted, and potentially they are excreted in the environment. So environmental harm from aquaculture can be quite high, and we really have to take care that these nutrients are handled in some way. So nutrient use efficiency, an increase in nutrient use efficiency means at the same time a reduction in the waste production of the system. And if we look at the nutrient use efficiency and use the formula that I gave earlier, we can see that for nitrogen, about 35% stay into the fish. This depends also a little bit on the nitrogen content of the feed and the feed conversion rate of the fish species in the given system, but it's around that every time. Same goes for phosphorus. And then we have different portions of phosphorus or nitrogen that go into soluble excretions and into solid excretions, where in nitrogen, it's a little bit more that is excreted in soluble form, like 58% of the content of the feed. And in phosphorus, it's about 50% that's excreted in soluble form and 50% of the excretions that goes into solid feces, meaning that 1/3 of the feed content goes into retention by the fish, soluble excretion and solid excretion. Now, this leads to nutrient use efficiencies of only around 30–35% for these main nutrients that we are looking at when we are evaluating aquaculture and aquaponics. And phosphorus is the one that's probably the most important, because this is a non-renewable resource that we really lose if we waste it to the environment. And it's much harder to produce than, for example, nitrogen, because basically we can only extract it from organic waste or from mineral resources that we can dig up and use. And once they are used, they are gone forever. So if we look at how aquaponics can increase our nutrient use efficiency, in general, we have the soluble part of the nutrients that is used by the plants. That's the idea of aquaponics. And if we look at the phosphorus that is soluble, this might be the limiting factor for plant production. So not all of the soluble excretions of the nitrogen part will be used if we don't interfere with the system, but let it run as it is. But we still can increase nutrient use efficiency of both nutrients to about 2/3, so 66%, which is already not bad, but we still lose about 1/3 of the nutrients to waste. And that's the point where we can think how we can further improve probably the aquaponic systems to also get to use the nutrients that are bound in the solid feces of the fish, because what we use here in simple aquaponic systems is only the part that is excreted in soluble excretions. So what's the potential of aquaponics and supplementary loops that we could add to our systems to improve nutrient use efficiency? One idea is to use so-called digesters to make the solid bound nutrients also available in the aquaponic systems for the plants. And if we look at the potential of improvement, we can see that we can use up to 81% of the phosphorus by using these systems and 79% of the nitrogen. So that's quite an important improvement again. And the different digesters that are available are mainly aerobic digesters, where we decompose the fish sludge using a lot of oxygen, and anaerobic digesters that in contrast operate without oxygen and break down the fish sludge into bioavailable forms of nitrogen and phosphorus that the plants can absorb. And all of these systems are already more or less well studied as standalone solutions in wastewater treatment, for example, and they exist in a lot of different sizes and ways, so that it's not very difficult to find a solution that might fit into our concept of an aquaponic system. Today, we will look a little bit closer at anaerobic digesters, and that's what's quite the expertise of my colleague Carlos, and that's why I think we should switch now over to him to have some say about his experience with anaerobic digestion.
All right.
Over to you.
Thank you very much. Hello, everyone. Yeah, I started doing anaerobic digestion, in fact, with Zala and Ranka, one of my first experiences. I did a 1 month stay some years ago at the CHV. Because of Michael was commenting you, phosphorus is locked. A good chunk of the phosphorus is locked in the organic matter, that it's in the feces and the uneaten feed of the system. And if you don't do anything about it, it obviously is lost to the plants in an aquaponic system. Of course, you can take that solids and you can apply it as a fertilizer elsewhere. But if you really want to recycle the phosphorus into a soluble form that plants can take, then of course you need to do something about it. So yeah, we knew about aerobic digestion for quite a while. It's a very simple way of doing this recovery. But you will see as we go into the next slides, there's the limitations of it, and then why anaerobic digestion may be also an option to look into. So can you go to the next slide, please? Yeah. So as you saw, about a quarter of the fish feed becomes feces, and that's a combination of feces and uneaten feed and some biofilms, right? This is what we are extracting with our mechanical filters or our solid traps, and then we have to do something about it. Again, the easiest would be to simply apply it on land, but then in many cases that is just not feasible. In cases where you're doing marine aquaculture, that is impossible because the sodium in the sludge will affect the soils, and then sludge becomes basically a waste that you have to dispose properly using authorized landfills for this. Again, complicates the issue. But back to freshwater, these are the two options that we have to use bacteria to make those nutrients available for plants. As Michael already explained, you can have aerobic digestion. And aerobic digestion is basically burning. It's an oxidation process. You slow burning organic matter for 15 to 20 days, and then whatever comes out of that is basically like a burn, is a stable sludge at the bottom of your reactors, which is basically ash for the most part. And the rest, what is left in the water, is something that you can use. And then anaerobic digestion is a more complex process. So aerobic digestion happens in an oxidative environment. That means molecules are giving away electrons, so they're becoming simpler and simpler and simpler. Anaerobic digestion happens in the opposite direction. It's a reductive environment, and molecules are gaining electrons and they're becoming more complex. And that happens in a way that there's basically four large stages mediated by four large groups of bacterial communities that do different things. And in the digestion process, one community takes over the next, and so on, until you get, in the end of the process, you get methane and CO2. And this is the typical biogas plants that you see being implemented all over the place, use this principle. Now, what we're doing in aquaponics is basically stopping the process midway to get what we want at the stage that we want. And this is a bit complicated because obviously if you don't steer the process correctly, you will go either backwards or you move all the way to methane production, and you don't want that in an aquaponic system. So to put it very simply, and if you go online or you check the literature, this is the typical description of the whole thing. You have a hydrolytic stage where bacteria start breaking down organic matter. Then you have an acidogenic stage where another group of bacteria start creating organic acids. And then those organic acids are used by yet another group to create formate and acetate and hydrogen. And finally, you have the methanogens, which take that hydrogen and create methane with the hydrogen that has been created. We are trying to stop this thing in the hydrolysis acidogenic stage. And I will explain you now in the next slides why is that. Please, next one. First, before that, I want to show you why do we think, or I think, the digestion process might be interesting, especially in larger facilities. And the main reason that I see for this is simply what you see there on the second row of this table is the sludge retention time. So in aerobic treatment, you need about 20 days, literally boiling the sludge with air in order for you to get the nutrients out of the organic matter. In anaerobic treatment, you need about 2 to 4 days. What does this mean? This means that imagine you have a farm that is producing, let's say, 1 cubic meter of sludge, liquid sludge daily as you go through your days. Well, if you need 20 days of retention time, you understand that you're going to have to fill up 20 cubic meters of the stuff, let it boil on air, and then you do something with that. Those reactors start getting very big. And the larger the farm becomes, those reactors start becoming huge. So if you see that you can reduce the sludge retention time from 20 to about 2 days, if you're good at it, then that means that your reactor effectively becomes 1/10 of the volume. And that has big implications when your farms are very big, or when you don't have a lot of room in your farm. So anaerobic treatment, basically, it's a more complex, high-tech solution that we're forced to take simply because things become so large, and often we just don't have either the money or the space to do such large structures when we look at aerobic digesters. There's another, I would say, side benefit of the anaerobic digestion process is that you can use some reactors, I'll show you later, that can retain the solids and separate the solids from the water continuously. So you're pumping in sludge, and sludge gets trapped, and clean water comes out all the time. And this is very useful because the reactor can run continuously. In an anaerobic system, because you're basically bubbling all the time with air, whatever water you take out without shutting down the diffusers or your aeration equipment, obviously is going to be a very turbid and dirty effluent that you have to treat more again. And there's a cost associated to that. Of course, you can shut things down, but then this batch process is definitely not continuous. You have to stop what you're doing, stop the aeration, wait for things to settle, move the water out, and so on. And what people do to create some continuity in this process is to have two reactors. So when one is working, the other one is emptying and clarifying, and then that is happening like that. Well, you have two reactors now, so you're paying for simplicity. So this is the main difference between the two processes and the implications, the operating and economic implications of selecting each process. And this is why I wanted to give you a bit of the importance of knowing this. Okay, next slide, please. So we go to anaerobic. We said, okay, aerobic reactors sure are simple, very easy to operate. They start becoming unpractical when they become large. Okay. How do we do it anaerobically, and how do we maximize solids retention? How do we maximize water clarity? And how do we try to keep things as small as possible? And there's a reactor concept or a reactor design, which is not new, which is called the upflow anaerobic sludge blanket reactor. It's all over the place. It was invented in the Netherlands and is being applied worldwide in wastewater treatment. So how does it work? You basically inject water at the bottom of this cylinder that you see here in the picture, and basically the water will rise up that column at a certain velocity. Why? Well, because water is an incompressible fluid. So the only way, if you inject more water, the only way, because the water cannot compress, the only thing the water can do is rise faster or move faster. This is a typical case for when you're designing pipes in systems. The good thing the easy thing about this is that if you know how fast the sludge sinks in water, then you can create a flow that is equal or less than the sinking velocity of the sludge, and therefore you can effectively trap the sludge there forever. Of course, sludge will have different particles of different sizes. Some of them will be lighter than others, and you will never be able to trap 100% of it. There will be small particles that will basically float away in the velocity. There will be floating matter, and that is because there's bubbles of gas being formed by bacteria, and those will carry, because they're sticky, they will carry up organic matter. And again, you will not be able to separate everything, but it does give you a really good way of controlling most of the sludge. So you end up with a column where sludge is at the bottom, clarified water is at the middle, and some layer of, let's say, foam, we call it scum, sits at the top. It's a 3-stage separator, basically. And that allows you to, well, pull the water from where the water is cleanest, meaning, let's say, 2/3 up of the reactor column. You can flush the scum separately. You can flush the heavy solids separately. And this way, you can control what we call the sludge retention time independently, largely, of the flow of water coming in. Which, again, if you have fluctuations in the sludge, in the flow of sludge coming into your reactor, let's say because you're feeding more or less in your system, or because this day, on a particular day, you were washing things out and you have more water being produced. If the reactor is dimensioned correctly, that sludge will simply rise a little bit or sink a little bit, but you will be able to keep it. And well, that's basically the brilliance of this concept. If you look at the picture there, you see that there are two manifolds, one midway and one on the upper. And these are basically pipes that are inside the reactor, where water of different stages can go out. So in the middle manifold, you got the clean water coming out. And in the top manifold is a foam, basically flushing manifold that if you open a valve, basically the foam and water will just rush out through those pipes. Next one, please. And this is some of the research we're doing at the moment, because as you saw in the previous slides, we're trying to grab the anaerobic process, the anaerobic reaction process at a particular stage, which is hydrolytic acidogenic. There in between, it goes a little bit back and forth, where the pH drops the highest. When pH drops, basically the availability of nutrients in a water full of nutrients changes, and you probably already know this, or you will know it knowing aquaponics and hydroponic technology. So there's a point in the digestion process where bacteria are producing organic acids, and therefore the water is getting acidified. And at that moment, there will be a change in the composition of nutrients being solubilized into the water. So we're trying to see what happens, literally, because some nutrients will change, some others will not change. Of course, our focus is phosphorus, that's the main one, but there's also other ones, micronutrients, that we might want to be looking at. So of the research that we are doing at the moment, you can see here, if you have sludge and overflow water. When we say overflow water, is the water coming out of the aquaponic system basically solids free, and you can see there at the left side of the slide the comparison in nutrient composition between raw sludge and overflow water. And overflow water is full of nitrate. The raw sludge barely, has much less nitrate, about less than a quarter compared to the other one. Phosphate, you can see that raw sludge has more phosphate than overflow water, and you can see manganese and iron. These are two nutrients where you're simply studying. You can see how they occur in raw sludge, but they don't occur in overflow water. So if we take that raw sludge and we take it through a typical digestion process, and when I say digestion process, it's not all the way to methane production. You need 20-30 days to get there. We're stopping at day 2 to 4 or 5 to see what happens there. Then you start seeing some interesting things. First, you see on the yes, Gertrude. Okay. If you look at nitrate, when you treat it anaerobically, it basically disappears. Why is that? This is because the sludge is carrying a denitrification process inside the reactor. So there's a bit of a drawback there. Some nitrate that you may have, or some nitrogen that you may have in your sludge, you will lose some of that during the denitrification process. The denitrification process happens very quickly as soon as the reactor becomes anoxic. As soon as the oxygen drops down below 0.1 milligrams per liter, heterotrophic bacteria will start taking whatever carbon is available and use that to denitrify. You lose the nitrogen relatively fast. But what happens with phosphorus is that from day 2, you can start seeing in the blue bars, which is a fully anaerobic process, you start seeing the concentrations going up. And if you bring that to day 5, you can watch the concentration has increased. So you're basically effectively solubilizing the phosphorus out of the sludge in a 5-day treatment. You can see on the red and green bars, these were other modes of digestion that we wanted to try. The red one was fully aerobic, and you can see nothing is happening there for phosphorus. In fact, the opposite is happening. You're losing dissolved phosphorus because bacteria are growing in an aerobic environment, and they're taking phosphorus out of the water to build up cell mass. And the same is happening in an intermittent aeration, let's say, method or mode, meaning this don't work. If you want to solubilize phosphorus in 5 days or less, you need to treat the sludge anaerobically. With iron, we had a very interesting result, which is it starts to solubilize at day 2, but then by day 5, it gets oxidated, so you lose it out of the water. And with manganese, you do get a solubilization similar to what phosphorus is doing. So these are our first, I would say, preliminary results of looking at what's happening with pH and how pH is affecting nutrient solubilization in this type of reactors. Next one, please. So what does this tell us? And again, I gave you those results on nutrients. We have done other work, for example, on studying how good the stabilization of the solids are. And the results, even though I don't show them here, you have to take my word for it. In many cases, the sludge becomes really thick, and the water that comes out of the reactor comes rather clean. So this obviously opens the possibilities to do many things. You can use this type of reactors to only denitrify. If you need to remove nitrogen out of the water, you can simply allow a sludge reactor to become anaerobic. You may have to add extra carbon, that is using molasses or acetate or acetic acid or vodka for that matter, a carbon source to it, and you can remove nitrogen very fast out of the water like this. Obviously, if you allow the sludge to digest for, in our case, up to 5 days, you will see that phosphorus gets solubilized. We see that some micronutrients will be solubilized. We don't know all of them. We only know so far manganese and iron. So research will tell us later what is the sweet spot for each of them and is it important or not. My favorite feature is this sludge thickening capability, because the sludge that comes out of your typical mechanical filters is less than 0.5. It's up to about 0.1 dry matter. So you can bring that up to 2%, even more dry matter. You're basically increasing your solids content or your solids concentration by 10 to 20 times just by putting the sludge in a reactor for a few days. I mean, this has economic implications. The sludge becomes a lot easier to thicken further or to transport or to do something with it. And the water that comes out is relatively clean. So you can polish it and reuse it. Some researchers and some companies are looking into methane production. So again, you will have to sacrifice some of that nutrient solubilization, but if your goal is to generate energy, to generate heat, then you can do that. And I put here as a long horizon out of a small research project that we did. We found through metabolomic methods, and this is basically methods in a similar approach to doing metagenomics, you do metabolomics, which is basically finding all the possible, let's say, metabolic compounds that are in a particular sample. And in this case, in the case of sludge, would be the metabolic compounds produced by bacteria in a sample of sludge. We found on our research project about 2,000 possible metabolic compounds, and in that massive database, we found many that are potentially interesting. We found potentially stress modulators. We found insecticides. We found fungicides, meaning natural molecules. So it opens a bit the door to, okay, is there something here from biorefinery perspective that we should be looking at, because there were many interesting things in that sludge. But that's a project that we have sort of parked on the side, but definitely it would be very interesting to look at in the future. I think that's the last slide from my side.
Yes. Yeah, thank you, Carlos. This was really a deep dive into details of anaerobic digestion and very, very interesting. Thank you a lot for that. I appreciated it a lot and learned also a lot of new things. Thanks for that. I would like to go on and have a look at how we could integrate anaerobic digestion in our aquaponic systems. Usually, oftentimes we are talking about 3-loop aquaponics if we are integrating anaerobic digestion into our aquaponic system, because we have these 2 loops that are usually there, like aquaculture and hydroponics, that are combined in an aquaponic system. And then the sludge treatment usually is a separate loop. That's why we call it a 3-loop system. That takes care of the sludge that comes from the solid removal unit of our aquaculture. And that's why it makes sense that our anaerobic digester is located somewhere downstream from the solid removal and the sludge removal from our solid removal components. And just to remind you of what we usually use in aquaponics as a solid removal device, there are some less sophisticated devices like sedimenters. Radio upflow filter is one example that's not very sophisticated. And that is oftentimes used to separate coarse particles from our aquaculture. And the sludge that is collected at the bottom of these sedimenters is what goes into our anaerobic digester usually. And on the other hand, we see something a little bit more sophisticated that filters also smaller particles out of the system. But also here, the sludge collected from the solid removal device would be what goes into the digester. And what Carlos already mentioned, the solid content of both streams is not really, really high, because in the radial upflow filter, by nature, there's the sludge removed using the hydraulic pressure from the water column above the sludge. So a lot of water comes out with the sludge removal. And the same goes somehow with the drum filter, because there we are using water to backwash the filter to clean it. And thus we also have a lot of water in the stream. And sometimes it makes sense to thicken this sludge stream a little bit before we feed it to our anaerobic digester, because otherwise we would just have too large a volume to feed to the digester.
I think you need to move on.
And the basic reactor design, Carlos already mentioned a little bit of it, is that you have a column, like a cylindric column, where you have the influent at the bottom of the device, and then the water going up while the sludge settles down at the bottom. And the effluent is taken out at the top of the water column. And oftentimes it's suggested that you have about 20 to 40% of the fish tank or production volume as a volume for your anaerobic digester, and height to diameter ratio of 4:1 or 5:1. And what we see here in our sketch is something that Carlos would probably not always need, because he stops his digestion process a little bit earlier. But if you're interested in collecting also the methane that might be produced in the upflow anaerobic sludge bed reactor, you would have something like we can see here to collect the upstreaming gases, the methane that you also want to make use of if you don't stop the digestion process earlier, but you're interested in collecting the methane to use it as an energy source. So the most important operating parameters that we have to take care of would be the solid retention time and the hydraulic retention time in our reactor. That might be for the solids 2 to 4 days if we don't want to go all the way to the production of methane, or a little bit longer if we are interested in producing this component too. The organic load rate, that might be about 1 to 2 kilograms of chemical oxygen demand per cubic meter of reactor volume per day. And that would mean that we need about 200 to 450 liters per kilogram of fish feed that we are feeding to our fish. The pH should stay in a relatively narrow corridor between probably 6.8 and 7.2. And also temperature is something important to take care of, because for good digestion, we usually need temperatures above 28 degrees, and the optimum is between 35 and 37 degrees. That's why in some situations we might have to take care of the temperature control also. So this is what we might have to look at in terms of operating parameters. And if we look at the nutrient concentration, I looked up some numbers that our partners from Ben Gurion University found in an experiment. And they were measuring the nutrient content of the supernatant of their UASB reactor. And we see that they have quite high nutrient contents in nitrogen, which mainly comes as ammonium. And also high amounts of phosphorus and also potassium. That might be surprising, but they explain this from the use of potassium carbonate as a buffer for alkalinity to regulate the pH of the reactor. And one thing we have to keep in mind if we are including this reactor in our aquaponic system is, especially with closed loop aquaponics, that we have a high content of ammonium in the supernatant of our reactor. So we really have to take care if we feed that back into our system, because this is very toxic for fish. So we either have to transform this into nitrate before it goes back into the system, or really add it very carefully, and preferable add it to the hydroponic part of the system, so that the plants can use a lot of this ammonia before the water goes back to the fishes. Oftentimes it's probably even the better idea to use this kind of device for nutrient use efficiency improval in decoupled systems, where the water don't directly flows back to the fish, to make sure that we don't have any toxic implications for our aquaculture. So this would be the main things we have to take care of if we want to integrate anaerobic digesters in our aquaponic system. And we can see that this has quite potential for the improvement of nutrient use efficiency in the aquaponic system. But there is a lot of research going on how to improve even further the nutrient use efficiency of the whole system. And this research looks mainly into the use of plant waste in anaerobic digestion. And this is quite a different kind of device that we need for that, because plant waste is mainly having a lot less water content than fish sludge. And that's why the device we are using for that looks also a little bit different from UASB. But it's more like the typical plant-based anaerobic digester that we know, for example, also from agriculture. So if we think that 23% of the plant biomass that's produced in our aquaponic system goes into waste, oftentimes like the roots or non-eatable parts of the plants. And here again, it depends on which kind of plant we are cultivating. For tomato, all the vines are not eatable, for instance, and all the leaves. So they might even have more plant biomass that is not eatable than lettuce. Then we quickly understand that there's another huge potential for nutrient recovery from these wastes that's probably as large as the potential from the fish sludge. So the mechanisms that go on in an anaerobic digester for plant waste are basically the same than in an upflow anaerobic sludge blanket reactor. So the steps that Carlos explained to us are more or less the same, but the amount of microorganisms for the different stages might be a little bit different, because in a plant waste anaerobic digester, the step to break down the fibers of the plant waste is much more difficult than in the fish sludge process. So the microbial community might be a little bit different, and a huge difference is also that oftentimes these reactors have to be mixed, because we don't have this mechanism of an upflow of a water stream where everything gets separated by itself. And that's why we have to steer a little bit more the content of these reactors. And we also have an outflow in terms of supernatants that's a little bit smaller compared to the volume that we put into the reactor, with consequences to the nutrient concentrations in the outflows. We will look at that in an instance. So plant waste anaerobic digesters come in all kinds of forms, as we already also saw for the fish sludge digesters. We have small scale plant waste anaerobic digesters. We have even scales that are meant for home use, with already integrated biogas collection in this bag here at the top that you can use for cooking, for instance. And all these different kinds go up to large scale plant-based anaerobic digesters that we know as biogas plants in an agricultural context. So also here, there are already existing all kinds of different reactors, and some of them might just be good enough to be used in the context of aquaponics too. And if you look at the nutrient concentration in the supernatant of a plant waste anaerobic digester, and I took here some numbers from Ben Gurion University again, we see that the nutrient content of the supernatant of a plant waste reactor is even higher than the one in the supernatant of the fish sludge reactor. That is mainly because the amount of water that is put into or fed into the plant-based digester is much smaller than in the fish sludge digester. And obviously, here again, you have to take care a lot of the ammonium content of the supernatant in the context of aquaponics. And that's why you usually don't feed this supernatant back to your aquaponic system, but you feed it into a separate hydroponics department where you can dilute the supernatant and add some missing nutrients to have a perfect nutrient mix for your hydroponics. But the potential that Ben Gurion University found out for plant-based anaerobic digestion is that you could more or less double the cultivation surface of your aquaponics system when you include also a plant-based anaerobic digester. And then finally, in the same experiment where I took the numbers for the nutrient content of the supernatant from, the colleagues from Ben Gurion University also looked into the carbon dynamics of the whole aquaponic system. And they found out that about 38% of the carbon that is in the fish feed ends in the solid phases. So the fish sludge that could be used for methane production. And the same goes for plant waste. And it's interestingly more or less the same amount of carbon that also ends up in the plant waste produced from this fish feed source. Right? So we have the nutrients that come from the fish feed in the aquaculture, and then the plants use carbon in their photosynthesis process, and that's how the carbon comes into the plant waste. So the carbon in the plant waste is not from the fish feed. That's why it's separated here in this diagram, but from air. But we see that from 1 kilogram of fish feed, we can produce 167 grams of carbon in fish feces and 155 grams of carbon in plant waste. And if you look at the potential for energy production from this carbon source, and assume that we have a carbon recovery efficiency of 65%, what's quite typical for anaerobic digestion if we go all the way to methane production. We can produce up to 270 liters of biogas for every kilogram of fish feed in the fish sludge digester, and about 310 liters of biogas from the same amount of fish feed in the plant waste digester, with different methane content in the biogas. But as a result, we produce a potential energy from 1 kilogram of fish feed of 2 kilowatt hours in our ASB and 1.9 kilowatt hours in our plant waste anaerobic digester. And oh, here I have a duplication. This means that in an aquaponics that includes anaerobic digestion for fish sludge as well as for plant waste, we have a potential of about 3.9 kilowatt hours per kilogram of feed we are giving. And in small scale aquaponics, this methane could be used for cooking, for example, if we are producing only produce for sustainable, for self-sufficiency, for example, or in larger scale systems, this can be used to increase the energy efficiency of our system and to produce a significant portion of the energy we need for the operation of our system. So still a lot of research to do in this context, but we see that there's a lot of potential to increase the efficiency of our aquaponics plants, and to go probably even a little bit in the direction of off-grid aquaponic systems that can produce all the energy they need by themselves if we add a little bit of solar power, for example. Challenges that we have to consider if we want to include anaerobic digestions in aquaponics are mainly the initial setup costs. So the required investments in the different digesters that we might want to have and the equipment and setup of them. Then we have to be aware that all of these digesters need regular maintenance and also monitoring for their optimal performance. And especially the pH should be in a narrow range so that we don't run into problems, as well as the temperature control that might be needed in some contexts so that we don't have negative impacts of temperature on biogas production and nutrient recovery. But on the other hand, we have a lot of benefits of anaerobic digestion in aquaponics towards sustainable and environmentally friendly solutions for future food security. Mainly, we have the benefit of enhanced nutrient use efficiency. We have environmental benefits like the reduction of reliance on synthetic fertilizers. We have minimized waste discharge and a reduced carbon footprint. Obviously, we also have economic savings because we reduce the energy costs when we use biogas, and also the reduced need for external fertilizer inputs. And we also enhance the system resilience of our aquaponic systems because we have our own source of nutrients and our own source of energy that contribute both to the resilience of our system. So at the end, I would like to come back shortly to our simplified and small and simple aquaponics that we were talking about also in earlier webinars, and present to you a very simplified solution for an anaerobic digester that can be included into small-scale aquaponics. I already presented a couple of times to you this low-tech solution for training systems for aquaponics and aquaculture that we developed in the context of our projects in Cities Food and Front Arc Nexus. And here we can see that attached to the fish tank, we have this radial upflow filter that is directly connected to our anaerobic digester here in the middle of our system. And what's important with this low-tech solution is that it's completely operated by hand. That means no automation. You have to be aware if sludge is collecting in your radial upflow filter, and if you have to clean the filter, you will by hand fill in the sludge into your anaerobic digester. So you have to open a valve and close it again if the sludge went out of the solid separator. And you also have to make sure that the head between the solid separator and your digester is high enough because the whole process is driven by gravity. So probably if you want to evacuate sludge from the solid separator into your digester, you have to evacuate some of the supernattant beforehand to lower the water level in your digester.
Yeah.
The main functionality of the digester is quite simple. At the start, when you first feed the digester with fish sludge, the main processes will be aerobic, and then some of the transformed fish sludge will come up to the surface of the digester with the different gases that are built with the metabolic processes. That's a little bit like what Carlos explained for the upflow UASB reactor, so that we create slowly a sludge blanket on top of the reactor. And this sludge blanket basically closes the underlying volume airtight, so that the remaining oxygen will be consumed quite quickly. And then the reactor switches into an anaerobic state and begins to work anaerobically. And that's why it's very important that this sludge blanket on top of your reactor always stays intact. So you should not feed the reactor from the top with pouring water or a sludge from the top, but you should always feed the reactor somewhere at the bottom or at the middle of your reactor, so that the sludge blanket on top stays undisturbed. And this goes also for the evacuation of the supernatant. That should also be in between these two sludge layers. You don't want to have any sludge from the bottom into your supernatant, and you don't want to have some of the sludge of your sludge blanket in your supernatant. So you also take out the mainly clean water from the middle of your tank. But from time to time, you might have to mix the sludge at the bottom. And also, if you do that, you will have to take care that you don't break the sludge blanket on top of your reactor. And most of these steps are already explained now in the slide before. But here's some example of a mixing device that you might want to use. It's something that you know from construction, that you can attach to a common screwdriver. And you could operate the reactor in a manner that you leave this here inside of the reactor all the time, so that you don't have to introduce it through the sludge blanket, but you only have to attach your mixing device to the top of your mixer, mix a little bit the sludge at the bottom, and then you're done without breaking the sludge surface of your anaerobic digester. So this would be a couple of hints regarding low-tech anaerobic digestion. And this also concludes more or less the webinar for today. I did not foresee for special homework this time, because I thought that this might be an opportunity for you to revise the balancing homework we had a couple of weeks before. So everybody who has not filed homework for this webinar could profit of this non-homework webinar this time to catch up with the homework I gave at that time. So thank you very much for your attendance. And might I hand over to Sala for a second?
Thank you very much to both of you. Does somebody have any questions?
May I?
Sure.
Hey, Carlos and Michael, thank you for the presentation. Is it feasible to use membrane bioreactor for treating the RAS system? Let's say like membrane bioreactor is aerobic process, but also anaerobic process. We can use it as well.
Yes, I can answer that. Yes, the short answer is yes. There's some interesting research by the excuse me, by the Freshwater Institute. Christopher Good and collaborators. You can look at it on the internet, where they've been using some MBR, anaerobic MBRs. Man, they recycle everything. It's really cool what they're doing. The only drawback, of course, is the maintenance of the membranes. What I have seen, and probably Christian also has a similar experience, is that if you do the UASB right, you get a relatively clean effluent. And so, man, you could probably use membranes as well, but then you don't have to deal with fouling of of the membrane, which is directly with the sludge. You can polish things, and then your treatment train is a lot cheaper and a lot easier to handle. But it can be used. It can be used.
Yeah, but the problem with the digestion, if something happened with if you don't have control environment, everything will be like ruined. Especially the sensitivity of the digester is very, very high. If there is something happen to the pH, the temperature as well, the microorganisms that break down organic material are also being affected by the temperature, and there's like multi-variable that could affect the entire digestion process, and it's a scary more. I mean, the MBR, you can avoid any certain problem slowly and also easily. And also the energy requirement for the MBR is very low, since you're working with very, very low pressure as well.
Yeah. No, you're right there. I mean, in my opinion, now you saw it on the presentation. You have to have unless of course you're doing something very low tech like was presented. But if you're doing something more commercial, you do have to have a monitoring system connected to the reactor. And what we use that we have redox probes, pH probes, temperature probes, and so on. And we have dosing pumps to control redox and pH automatically in the reactor. To keep it from steering all the way, to where you do want it to go. So that is true. The membrane will effectively have a firewall against something that could go wrong there. You're right. Yeah.
There's
Hello,
another Gertrude with a hand up.
Everybody's Gertrude.
So Gertrude number 2, any questions? Or I don't even have them numbered, so.
Yeah, there's a user with a hand raised. That person can unmute the microphone and say something. And there's two.
Oh no, there are 2 Gertrudes.
Yes.
I can ask one Gertrude to unmute. Yeah.
Okay, maybe I'm one Gertrude. Since boss decided to give us our name for today, so we are happy to share that name for today. Hello, Carlos.
Hi, Gertrude.
No, this is Julius, not Gertrude. I just say thank you for a very wonderful presentation, which was overlapped by Michael. Makes a great deal of sense. In your presentation, the reactor which you presented looks a bit bigger, which I think may be quite expensive to deploy in a research aquaponic system. I just want to know if we have these reactors in different sizes and prices. And also, before I wind up, I also want to really see that there are lots to benefit from based on the research that is ongoing, that even from the waste, there are other beneficial products that can come out of digesting the waste. I pick one thing, which is like at the end of the research, the world will be lucky to even derive what we call it, bio drugs, waste for the treatment of the fish itself. So I think it's something to pay particular attention to. I wish the researchers good success. It's a bit complex, but I know at the end of the tunnel there will be some elements of light. So regarding the sizes and the prices, do you want to comment briefly on that for the reactors?
Yes. To give you a very, very, very rough rule of thumb on the reactors that we're doing, they are not super large, but they are not small either. They cost about, I would say, very roughly, about €1,000 per cubic meter of reactor volume. So a large 10 cubic meter reactor will cost about €10,000. And so on. If you go bigger, that probably will get cheaper because of scale. But at those, I would say 10 cubic meters and less, we are about that. That's and that's the complete reactor with monitoring systems and automation and the whole thing. It's a very plug and play thing. They are not cheap, but they're not too expensive either compared to all the things I've seen in the market.
Thank you.
Another Gertrude? Otherwise, we have Emmanuel.
Okay, so maybe since the other Gertrude is yet to come online, I will use the opportunity. Thank you all. I got a little mixed up, or maybe need for some clarity. For those of us who are quite familiar with the Institute's food system aquaponics model, I think Zala and the team had what we call the mineralization tank, which also works maybe under anaerobic conditions. So with this one that Michael just talked about, I don't know if it is an add-on or it is similar to that of the mineralization tank, since they seems to be both doing the same thing. I would need some clarity on that if there is any explanation to that.
Yeah, it's the same. Simple answer. So I was talking about exactly the mineralization tank that we have included in the training system. And it's basically the way we are operating it, an anaerobic digester. So it's just synonyms.
Okay, because that one, I think until today, I wasn't really conscious about that blanket on top that you talked about, that we needed to break it. So that is what I really wanted to be sure of. So thanks.
Someone else? Okay, then I would then thank you both again for this nice webinar and everyone to join us, especially a lot of Gertrudes today. And at the same time,
Hello, Zala. I have been raising my hand, Zala.
Oh, okay. Then I let you talk.
Is it not showing my name?
No,
It's
I
not
don't know.
showing my name, really?
But you have really bad internet connection.
Is it showing as Gertrude?
Yes, you are still Gertrude, yes.
Oh, so you're not getting me?
Yeah, well, I mean, now it's okay. Now we know that it's you. Now it's okay.
Hello? Go ahead. Okay. Now, okay. Now, yes, I really appreciate the presentation. It's full of information, and it's a very, very microbial composition of the sludge from the Institute's prototype that we have here. But one thing that I've noticed is because we try to look at it from 7 days data, which probably very soon we'll be able to
present some of the things that we observe. But one thing that I've observed is the sludge in the system. We took the sludge from the system and then we try to also subject it further to anaerobic digestion, so we can break down the component a bit down more and then have more minerals coming up. But from a scientific background, what we have in that digester is a composite of the sludge that have accumulated over time. So somehow it's difficult to link it to one day or 2 days or 3 days, because it has been there for quite some time. So, well, it creates a kind of composite situation of sludge that have accumulated over time, and then we can do that.
Unfortunately, the
We-
internet is not good enough.
That's the way we got reducing, because some of the
I probably also you two did not catch anything, right?
No.
No,
Sorry.
it got disconnected, but I think what he was asking is actually about the retention time, how it's calculated, I think.
I mean, if he refers to our training system, I would not really stick to some retention time. We should respect. I would just go with the needs of the system. So when we need to clean the radial upflow filter and we need space in our mineralization tank, I would just take out a little bit of the supernatant and make enough space and then leave the sludge inside of the reactor as long as it can. Because, yeah. Or, I mean, from my point of view, there are no backdraws that we could leave sludge too long inside of the reactor.
I mean, it's just at the end that it's a problem if you have, for example, too many solids, right? So at one point you have to replace part of it. So you take parts of it out. So that's the biggest problem, especially in these low-tech low-tech mineralization tanks, right? We have one way it's doing it the same as Carlos does, where everything is automated and everything is controlled. But unfortunately, this does not work in Africa. So I would try to do there really, I have to calculate my hydraulic retention time, what's my, how much sludge do I put in, how much sludge should I take out? And then at one point when you have too many solids, you have to take part of it out and replace it with the water.
Yeah. You can do that flow basis, as you're saying, is if you assume that your sludge is just, again, it's a volume of water that goes in and out, and you can calculate how much you're producing every day and how big your tank is. Then you know if your sludge if you're producing 1 cubic meter of sludge per day and you need a 4-day retention time, then you know that you need 4 cubic meters of tank volume to hold that. And then eventually after the 4th day, what you will do is that every day you purge some of that sludge out as new sludge comes in, and that should give you that will be the simplest way of doing it. If you want to be more accurate, then you can do it on a kilogram or mass, or let's say kilogram of dry solid basis, where you can catch your sludge samples, dry them up, see how much kilograms of sludge you have after you have evaporated all the water, and then run your calculations based on that as well. So that would be the correct way of doing it, but we know that in practice many things work by diverting a little bit out and keeping it a bit simple. So
yes, but from this point of view, if you're talking about the volumes, I think that in this little training system that we have, the mineralization tank is rather too large. Yeah.
yeah. So you have plenty.
Don't
Yeah.
have an issue with retention time being too small or something.
Exactly. You're not running out of space. True. Yeah. Yeah, we did some experiences with Zala with some reactors that I don't remember. The sludge was there for months, and it was all fine. The only drawback was the sludge becomes so thick that it doesn't flow well through the pipes. That's really the only thing. But if your pipes are more than, I would say, 32 millimeter in diameter or 40 millimeter diameter, the sludge will flow most of the time. So
we work mainly with 32 millimeters because that's what's available.
Yeah.
Any other questions? I think now there is no more Gertrudes with the hands. So with this, I would like to thank you very much. And then see you in 14 days. And at the same time, I would like to ask you, since this time we do not have homework, that maybe if you have some further questions that you would like us to answer on the last webinar, because the last webinar is actually an open session, that you let me know if you have some questions, and then we can maybe have a look at those. But we would need them in advance so we can also prepare a bit on those. So thank you very much, and then see you in 14 days. Bye-bye.
See you.
Bye-bye.
Ciao.